Welcome back to Plant Developmental Biology course. In today's class, we are going to discuss about flowering. So, flowering is basically a transition from vegetative phase to the reproductive phase in the life cycle of a plant. So, when your plant start post embryonic development after seed germination, at a certain time period or up to certain period of time in the life cycle, they only continue the vegetative growth, and that is the period when they make branches, they make leaves, and then at a particular time point in their life cycle, a major decision is being taken place, where what happens that this vegetative plants basically enters in the process of called floral transition, at it start the reproductive phase. And this is very important in the life cycle of the plant, because reproductive phase of the life cycle ensures the sexual reproduction, and sexual reproduction is one of the highly evolved mode of propagation in case of higher plants. So, the sexual reproduction is restricted in an organ or in a part of the plant which is called flowers, which are developed on a structure which is called inflorescence. So, in today's class we are going to discuss how this transition occurs, what are the genetic and environmental factors which basically regulates the timing of the transition, and once this transition has ensured, how a special organ which is flowers with a special structure and with a special organs like sepal, petals, stamens and carpels are developed. So, if you look, it is very important to understand that during the vegetative process, reproductive phases are repressed, and it is important because plant has to gain a certain amount of strength before it enters in the process of reproduction. There was a gene identified which is called TFL1. TFL is basically terminal flower 1, and when a mutation or when a mutant was identified in this gene, there was few phenotypes. One phenotype is that the plant flowered early. So, basically normally if a plant take a certain amount of, this is Arabidopsis thaliana. So, if normal Arabidopsis thaliana takes, let us assume some time period, for example 40 days to flower, basically this plant flowers much before. This is another mutant which was early flower mutants. But another things what you can look and see in the terminal flower mutants, that one thing is that it flowered early, but there is some special structure. So, basically these branches are getting terminated with a single terminal flower. So, this means that in the life cycle of model dicot plant Arabidopsis, you can look during the vegetative phase, these leaves are basically formed which is called rosette leaves, and then after transition the shoot apex get converted into inflorescence meristem, and this inflorescence meristem has a mixture of property. So, if you look the branches which are coming from the inflorescence meristem, they have indeterminate nature, whereas on the branches if you look this floral organ or flowers, they are determinate in nature. What it means that branches can grow and they can make many flowers, but once a flower is made, the meristematic activity is terminated. But here if you look the TFL mutant, what is happening that the shoot like structure get terminated with a single determinate flower. So, this was the phenotype which was observed in TFL1 mutant. This is the top view or upper loop if you look this region. So, you can see here that here the growth basically stops in a way, and there is not many flowers are made in this case. So, this is important, which suggests that TFL1 could be one important gene which basically repress the flowering, which is a negative regulator of flowering. On the other hand, if you look another gene or another mutant which is called leafy, leafy is activator of flowering. So, if you have leafy mutant, what happens? So, basically if you look in the Arabidopsis thaliana plant, so there are basically 3 types of structure. Type 1 rosette, and then there is a transition from here to here. This is the transition which we call about the floral transition, and here the first few structures which you look like here, they are called coflorescence. They bears a bract like structure, and then if you come to the higher side, there is a flowers which is without bract like structure. So, this is a typical architecture of Arabidopsis inflorescence, but in leafy mutant what is happening that you can see this schematic diagram here. So, in wild type you have this co-fluorescence and then you have these final flowers, but in case of leafy mutant the co-fluorescence are fine, but the later flowers which are basically getting converted like shoot like structure. So, basically there is a loss of floral identity. So, which suggests that leafy is important. So, if you consider these two processes, the entire and complete process of transition from vegetative shoot apical meristem till the flower, which has two stages, and this final stage is regulated by leafy. And this you can see here if you look the expression of leafy. So, you can clearly see that expression in the inflorescence meristem, which is on the apex, is very low or not detectable, but if you look the flowers or floral primordia, which is basically originated at the peripheral region of the inflorescence meristem, it has a very high amount of leafy expression. This suggests that leafy gene is very important in giving identity to the floral meristem. When you do not have leafy, this meristem is basically not acquiring floral meristem identity. Instead of that, it looks more kind of inflorescence meristem identity. And another interesting thing, if you look, so this is the side, if you look here from where the structure as or the expression of leafy is very low. But in TFL mutant, what is happening that this the side region from where your branches are coming, you can look here that expression of leafy is very high, and that is important because when you have high amount of leaf expression here, it will convert this meristem to floral meristem identity. This also proves that TFL and leafy they looks opposite. So, TFL is maybe more important for giving shoot identity or shoot like structure inflorescence identity, whereas leafy is important for giving identity to the floral meristem. And the critical balance between them basically ensures the time of transition and the identity of meristem. So, if you look this process, so you can place TFL is here, which is regulating even the first step of transition, and then leafy is ensuring a proper floral meristem identity in the peripheral region. And these are some other mutants, the typical schematic diagram of the mutant. So, this is wild type, and if you look the leafy like structure, you can see that there is a defect in the floral meristem identity. Another gene which is epitela 1, which is AP1, this is another important gene which is responsible for giving floral meristem identity, and it together with or in parallel with leafy both are working to ensure the floral meristem identity. And important thing that if you have double mutant of leafy and AP1, you can see that phenotype of both leafy as well as AP1 mutant phenotype is enhanced, which suggests that they are working into parallel pathways. And this is your terminal flower. When you have terminal flower mutant, you have a terminal flower. And another thing what you look, if you overexpress leafy, it looks like that it is mutant of terminal flowers. So, all these interaction basically suggests that leafy and AP1 they are very important factor in giving floral meristem identity to the peripheral meristem developing at the inflorescence, and TFL is a negative regulator of floral meristem identity. So, essentially if you summarize this process, then what you can see here that if you look expression pattern of TFL1, so in during vegetative phase it is expressed here, but in the reproductive phase after floral transition it continue expressing in the inflorescence meristem, but none of the floral meristem or developing floral primordia show any expression of TFL1. Whereas if you look leafy, in leafy what happens that the inflorescence meristem or the center of meristem does not have leafy expression, but the peripheral region where your floral primordia is going to be initiate, they have very high amount of leafy expression, and this expression continues in the developing floral primordia. AP1 has a quite overlapping expression pattern like leafy. So, you can see that in the very early floral primordia you have AP1 expression, then at the developing floral primordia you have a high level of expression. At the later stage the expression is restricted to the first whorl organ, which in case of flower is sepals. So, what happens actually? So, at the center, if you look this region, in the center you have high amount of TFL1 expression, and you do not, you have very low or less amount of leafy expression. And when you have high amount of TFL goes and it repress both AP1 as well as leafy in the center region. And since you do not have leafy, you do not have AP1, which means that you cannot assure any floral meristem identity in the center. So, that is this helps in maintaining inflorescence meristem identity at the apex. But if you look the peripheral region, just here in the peripheral region your leafy is getting activated, and when leafy is getting activated, leafy also activates expression of AP1, and then both leafy and AP1 together basically specify or provide identity, floral meristem identity to the peripheral meristem. On the other hand, they also they repress TFL1 in the peripheral apex. See, the interaction between leafy, AP1 and TFL, particularly the antagonistic interaction between TFL and leafy, TFL and AP1 ensures inflorescence meristem identity in the center as well as floral meristem identity in the peripheral region. If you summarize this interaction, so during vegetative phase and the inflorescence meristem you have TFL1 level very high, and then during floral meristem stage you have leafy, AP1, AP2, AP2 is another A class of genes which you will see. If you look the transition from vegetative meristem to inflorescence meristem, in the inflorescence meristem you have expression TFL1, AP1 and leafy are in the peripheral meristem, and these peripheral meristems are giving floral meristem. What happens if you have TFL1 mutants? So, since TFL is a negative regulator of leafy, so if you do not have TFL here, the leafy will start expressing here, AP1 start expressing here. So, all three central and peripheral meristem all are going to take floral meristem identity. On the other hand, if you do not have leafy, then TFL is going to expand its domain in the peripheral meristem, and since you have high amount of TFL1 in the peripheral domain, basically it will provide inflorescence meristem identity. Similar kind of things you can look when you have double mutant of AP1 and AP2. Here you have TFL1, so it will be inflorescence meristem, but in the peripheral region you do not have AP1, which means that TFL level will also go very high, and leafy is alone cannot specify full floral meristem identity. So, you will have essentially inflorescence meristem identity. So, this regulatory network or this interaction is very crucial in giving a clear floral meristem identity at the peripheral region of the inflorescence meristem. But what are the genes which are basically deciding that what is the time when this identity should be given, when this transition from vegetative to inflorescence meristem, when the vegetative shoot apical meristem changes its fate and identity and becomes inflorescence meristem. And definitely there is a floral repressor, there is a strong, this is a hypothesized when it was given in 1995 when the plant developmental biology was still at the early stage, and people have started looking very carefully plant developmental biology. So, at that time it was hypothesized that there has to be a strong repressing signal during the vegetative phase and how to acquire the reproductive phase. So, one thing is that one mechanism could be if you repress the repressor, that will basically activate the flowering, or if you start a new activator of the flowering. And when you look all the data, when you look the mutants identified or the genetic networks, you will find that both pathways exists to ensure flowering at a particular time period. So, for example, if you look, there is a constitutive repression based mechanism, and basically it has a TFL in it, and they basically activate, or they strongly activate this process of the floral repression during the vegetative phase. But you have long day promotion pathway, basically day length is very important in long day plants to ensure the flowering. Then apart from that, you have some negative regulators, you have gibberellic acid, which is playing very important role in deciding the flowers. And more than that, if you look here, there is a large number of genes has been identified. If you have mutation in that, either they show late flowering phenotype, early flowering phenotype, and there are conditions, if they can be long day condition, short day condition. So, if you look all those genes and try to understand the genetic pathways, or what are the regulators which basically ensures this process, then what you will realize here. So, these are the 4 major pathways which are important for regulating the transition. So, if you recall previous slides, then you will realize that these 2 genes, which are basically floral meristem identity genes, they are very important, AP1 and leafy. So, one thing what you have to do, you have to first ensure activation of AP1 and leafy in the peripheral meristem to ensure a proper flower development. The first step is this one. So, whatever gene can activate AP1 or leafy 1, they will basically promote the flowering. And the activity of leafy 1 and AP1 is regulated by 2 another important gene. One is FT and second one is SOC1, and these genes are called flowering time genes. So, and both are positive regulator of AP1 and leafy 1. So, if you want to ensure flowering, so FT and SOC1 has to be activated. But under normal condition or under vegetative growth condition, what happens that both of these genes are kept repressed by a repressor, which is FLC. So, if you look, FLC is basically negative regulator of FT and SOC1, and when there is a proper signal, then what happens, if you have a proper signal, then the repression of the FLC is repressed. So, you have 2 pathway, one is basically sensed by the gibberellic acid pathway, where plant hormone gibberellic acid is very important in activating flowering through this one. And another important thing, if you look, gibberellic acid can activate leafy directly, okay. But other pathway, if you look, the photoperiodic pathway, they are activating, they are positive regulator of FT and SOC1 through CO. CO is constant. So, basically when there is a suitable photo period, when there is a time, when there is a correct photo period, then this pathway will be activated, and this pathway will activate expression of constants, and then constants will go and activate FT and SOC1. But another 2 pathways, one is the autonomous pathway and the vernalization pathway. These 2 pathways basically, when they are suitable or when they are promoting the flowering, when they are in the condition to promote the flowering, what they does, they repress the FLC expression. So, FLC is a negative regulator of FT and SOC1. So, if you negatively, if you repress FLC, essentially you are activating FT, you are activating SOC1. So, when all the conditions, for example, if you took Arabidopsis thaliana, Arabidopsis thaliana is a long day plant. If day length is long day, if all the autonomous signal means plant is at the right age, right strength, and then vernalization signal is positive, if everything is okay, then all this pathway will activate eventually AP1 and leafy through FT and SOC1. And once AP1 and leafy is activated, just now you have seen that, then the meristem identity, the meristem which is basically coming at the flank of inflorescence, will take an identity of floral meristem. So, there is a switch, there is a change of the identity. So, during vegetative phase you have shoot apical meristem, then after transition this shoot apical meristem changes the identity and it becomes inflorescence meristem. When it was shoot apical meristem, then the peripheral Pramodia, they were basically leaf Pramodia. But when they become inflorescence meristem, then same peripheral Pramodia or the peripheral Pramodia which is coming here, if this is inflorescence meristem, it will become floral Pramodia. And how it will become floral Pramodia? Which means that it has to activate some floral Pramodia specific genes, and some of the genes which are very important in regulating the floral organ patterning. If it is floral Pramodia, it is going to make flower. If it is going to make flower, it has to develop flower specific organs, and flower specific organs are basically sepal, petals, stamen and carpels, and this job is done by a class of genes which is called A, B, C and E. These class of genes are very important, and these genes are called floral organ identity genes. They basically specify or they provide a proper identity to each organs in the development. And another important thing, if you look here, all these genes are basically getting activated later on by leafy and AP1. So, if you look, AP1 is getting activated by leafy. AP1 is dual function gene. So, it is floral meristem identity gene, at the same time it is also A class gene which is responsible for sepal development, which you can see in the later side. So, basically leafy activate AP1 A class gene, leafy together with UFO activate B class gene which is AP3 and PI in Arabidopsis, and leafy together with Ushal activate agamous AG gene which is basically C class genes, and then you have another set of genes which are called E class gene. So, if you look this transition process, so how it occurs? Another important thing to mention here, that the most of the signals are getting received in the leaf, and transition of the flowering or the decision to change the meristem fate occurs at the apex. The question is that how this signal which is being received in the leaves are getting communicated to the apex, and there is a long distance signaling involved here, and one important molecule which is FT, which you will see basically it is a mobile fluorescence. This is a signal FT can move from leaf to the apex. So, FT is getting activated in the leaf, and then it basically moves through the vascular tissue precisely through the phloem, and when it reaches to the apex, in apex it basically activates the gene. So, if you look here this diagram, so this is your leaf and this is your apex. So, in leaf what happens, FT is kept repressed by several mechanisms during vegetative phase. So, you can leave there are multiple mechanisms which are repressing FT, but when there is a photoperiod or right signal, photoperiod is basically activating constant and constant is activating FT, and when you have FT and other pathway like vernalization pathway, autonomous pathway, gibberellic acid pathway, they are also working to activate the FT, but they are repressing the repressor. So, eventually if you look here, FT is getting activated in leaf, and then it is moving through the phloem to the shoot apex. Once it reaches to the shoot apex, it basically interact with another gene called FD, and these two are very important, and they in the apex, if you look here in the center of the meristem, they activate SOC1, they activate agamous like 24, and the interaction between SOC1 and agamous like 24 along with the SPL9 genes are very important in maintaining inflorescence meristem in the center. But at the flank region or at the peripheral region, these pathway or these mechanisms, they activate leafy, they activate AP1, and then leafy and AP1 are interaction between leafy 1 and AP1, and then repression of TFL in this region essentially ensures floral meristem identity to this peripheral region. So, there are three classes of genes A, B, C, and how they express. So, they express in the overlapping manner. So, A class gene, they get activated in the sepal and they continue in sepal and petal Pramodia. B class genes get activated from petal and it is in petal and stamen Pramodia, and C class genes get activated here in the stamens and carpal Pramodia, whereas E class genes are basically expressed everywhere. So these genes are very specifically getting activated, and leafy is involved in activities these genes in a very specific domain. So as I said, if you look here, leafy activate AP1 in the region of the meristem which is responsible for, which is basically sepal and petal zone. Then it activates B class gene which is AP3 and PI in petal and stamen zones, and then it activates finally C class gene which is agamous in the carpal zones. So function of leafy is not only to give meristem, floral meristem identity, but also to ensure that downstream processes of floral organ patterning is also getting activated in a very specific manner or in a very domain specific manner. And if you look here, so basically this is the expression pattern of AP1, you can see in the developing sepal and petal pramodia. If you look agamous, it is only in the center, and if you look AP3, it is basically in the domain where you have petal and stamen pramodia. And if when you overexpress leafy one, you can see that expression domain of all these genes are getting expanded. So this is just expression pattern of these genes at early stage and when there is a flowering. And then if you look the E class gene is very interesting in a way that it works like a cofactor for A, B, C class genes. So and there are 4 E class genes, sepaletta 1, 2, 3 and 4, and if you look the expression pattern, so basically sepaletta 1 and 2 is quite broadly expressed, but sepaletta 3 and 4 basically expression is restricted. And how they regulate the organ, which is important. So this is overview of the expression pattern. A class gene in the sepal, B class gene you have in the petals and stamens, and then C class genes you have in the center. This is A plus B plus C class gene. So you can have this kind of specific and overlapping expression pattern, and this is very important because their interaction, their overlap basically defines the identity. So if you look sepal, in sepal you have only A class gene and E class gene. So A class gene is here, B class gene is here, C class genes are here, E class genes are here. So if you look this region, only this region which is going to make sepal, it has only A class gene and E class gene, and this interaction basically gives sepal identity. In petals, if you look, this is petal. In petal you have B class gene, A class gene and E class gene. So you have A, B and E, and these 3 genes together ensures petal identity. Similarly, if you look in the stamens, stamens has B, C and E. So you have B, C and E, and this gives stamen identity. And in very center where you have the carpel, you have only C and E, and C and E together ensures carpal identity. In sepal you have A, E interacting, in petal you have A, B, E interacting, in stamens you have B, C, E interacting, and in carpel you have C and E interacting. And this you can see here, if you have mutant in this, what happens. So in the wild type pattern, the pattern is like that. And another important thing here is that A basically restricts the domain of C, and C they are mutually antagonistic. So they are restricting their domain. So if you have A mutant, A class mutant, what happens that the restriction of C disappears and C can continue expressing here. So if you look here, so this region is now it is having C and E, and C and E will give carpal. Then you have B, C, E, it will give stamen, B, C, E, it will give stamen, and here you have carpal. So if you have A class mutant, you can clearly see that your flower will have carpal, stamen, stamen, carpal. Similarly, if you do not have B class gene, then you are going to have sepal here, carpal, carpal. This you can see here, you have the 2 walls of the sepal and then 2 walls of the carpal. Third important thing, if you have C class mutant gene, what happens that A class gene will now continue expressing here. So here you have A and E, it will give sepal, A, B, E, it will give petal, A, B, E, it will give petal, and here you have only A and E, it will give sepal. But another important thing here, what happens that this structure basically continued. So, there is a flower within flower phenotype, which tells that in these mutants the floral determinacy is lost. So, normally what happens in the wild type, when your final organ, which is carpel, when carpel is made, the organogenesis is stopped, and that is called the state of determinacy. But C is ensuring that determinacy. If you do not have C class genes, so apart from the floral organ defect pattern, but you also see a loss of floral determinacy. But important thing, if you do not have E mutant here, E gene, so basically sepleta 1, 2, 3, 4. So, if you have mutant for all of them, although A genes, B genes and C genes are fine, but they cannot function, which means that their activity is dependent on E class gene, and in this case you can see that all the walls are going to have leaf like structure. So, this is clear that the activity and interaction between A, B, C and E is important for regulating floral identity. So, these are different organ patterning. So, you have inflorescence to floral meristem, these are the different steps. Then in the floral meristem you have the concentric ring formation, sepal, petal, stem and carpel. Then at the same time there is a symmetry broken, you have organ growth and then maturation of the organ. So, these are different stages of the flower development, and then you have different genes which are regulating different stages. The final thing which is important is the floral determinacy. So, as I said that flowers are determinate in nature. So, they basically terminate once final organ, which is carpel, is made. And you can see here, if you look the expression of usual, which you have already studied in previous classes, that usual and clavata, they are very important regulator of the stem cell activity. And in flower what happens, that at early stage there is a strong usual expression and a strong clavata 3 expression, but once the flower is mature you can see that usual and clavata 3 expression is almost disappear. But if you have agamous mutant, which is basically C class gene mutants, where you have the organ defect as well as determinacy defect, you can see even at the late stage the expression of usual and clavata 3s are maintained, which suggests that the determinacy is lost because there is no stem cell termination mechanism. So, under normal condition what happens, at early stage you have usual and clavata on. At this stage if you look, usual and clavata, and they are basically maintaining stem cell pole in the center, and that is why there is a indeterminate growth. But at the later stage, when this flower is in the process of organogenesis, leafy and usual together activates agamous in the center, and this agamous is responsible for carpel and stamen identity. But at the same time, at the later stage, when the identity of carpel is already established, this usual activate a gene called KNU, and this gene basically goes and repress the usual. And this is important factor. Once you repress the usual, there is no usual. There is no usual means there is no clavata. Once the usual clavata signaling pathway is lost, then the center region cannot maintain the stem cell niche, and that is why the growth terminates. Apart from the usual and clavata, cytokinin is also playing very important role in maintaining the stem cell pools. And you know that this is the biosynthesis enzyme, cytokinin is having a positive role on the stem cell maintenance. At early stage, this important auxin response factor, which is ARF3, which is kept repressed, but at the later stage this ARF3 is getting activated by auxin. Auxin is very specifically getting activated in the carpel at the later stage. So, carpel has auxin, once auxin is there in the carpel, it activates ARF3, ARF3 goes and repress the cytokinin signaling pathway, and eventually that repress the usual expression domain. So, this complex mechanism, all these regulators together ensures that at the end of floral organ patterning, the meristems are getting consumed up and there is no mechanism to maintain the dividing cells. Thank you very much. We will stop here, and in next class we will discuss about the cell-cell communication in plants. Thank you.